Welcome to Fun Facts Online. Imagine you could walk straight through a solid wall. In our world, that's the stuff of fantasy. But at the smallest scales of reality, in the quantum realm, this impossible feat is not only possible, it's essential to the universe. This phenomenon is called quantum tunneling, and its story is a journey from a bizarre theoretical idea to the cornerstone of a technological revolution that culminated in a Nobel Prize and promises to redefine computing itself. In the heart of the quantum realm, where the familiar laws of classical physics dissolve into a sea of probabilities, lies a phenomenon so counterintuitive it borders on the magical. This is the story of how a bizarre quantum leap evolved from a theoretical anomaly into the foundation of a new era. To understand this monumental achievement, we must first journey back to the early 20th century. The rigid deterministic universe of Isaac Newton, where every action had an equal and opposite reaction, was beginning to crumble. New discoveries showed that at the smallest scales, reality was fuzzy, uncertain, and deeply strange. One of the most radical new ideas was wave-particle duality, the concept that entities like electrons could behave both as solid, tangible particles and as diffuse, spread-out waves. This wave-like nature is described by the Schrödinger equation, and its solution, the wave function, doesn't tell you where a particle is, but rather the probability of finding it in any given place. It was by exploring this equation that German physicist Friedrich Hund stumbled upon something astonishing in 1927. Picture that ball and wall analogy. According to classical mechanics, if the ball doesn't have enough energy to go over the wall, it will always bounce back. The wall is an insurmountable potential energy barrier. But in the quantum world, the particle's probability wave doesn't just stop dead at the barrier. It decays exponentially as it passes through it. If the barrier is thin enough, the wave function still has a value on the other side. This means there is a non-zero probability that the particle will simply appear on the other side of the wall, without ever having had the energy to climb over it. It's as if it passed ghost-like through the solid barrier. This wasn't just a mathematical curiosity. It was the key that unlocked long-standing mysteries. In 1928, George Gamow used quantum tunneling to provide the first explanation for alpha decay, a type of radioactivity. An alpha particle is trapped inside an atomic nucleus by the immense strong nuclear force, creating a potential barrier. Classically, it shouldn't have nearly enough energy to escape. Yet through quantum tunneling, it has a small but finite probability of appearing outside the nucleus. This was the first major application of the theory and provided powerful evidence for the new quantum mechanics. Even more fundamentally, quantum tunneling is what allows our sun to shine. The temperatures and pressures in the sun's core are actually far too low for protons to classically overcome their electrostatic repulsion and fuse together. It is quantum tunneling that allows them to get close enough for the strong nuclear force to take over, initiating the fusion process that powers our solar system. For decades, tunneling remained a feature of the nuclear and astrophysical realms, but the 1950s and 60s brought it into the lab. In 1957, Leo Esaki demonstrated electron tunneling in semiconductors, inventing the tunnel diode. A few years later, Ivar Giaever showed tunneling in superconductors, materials that conduct electricity with zero resistance. It was in this context that a 22-year-old PhD student at Cambridge named Brian Josephson made a revolutionary prediction in 1962. He theorized that in a device made of two superconductors separated by a thin insulating barrier, pairs of superconducting electrons, known as Cooper pairs, could tunnel across the barrier as a collective coherent current, even with no voltage applied. This device became the Josephson junction and the phenomenon, the Josephson effect. For this work, Josephson, along with Esaki and Giaever, would share the 1973 Nobel Prize in Physics. What was so profound was that the Josephson effect wasn't just one electron tunneling at a time. It was the coordinated phase-coherent quantum behavior of trillions upon trillions of Cooper pairs, all acting as a single entity described by a single collective wave function. This was a macroscopic quantum phenomenon. It opened the door to a new, audacious question. If this vast collection of particles can act as one quantum object, could the entire macroscopic system tunnel through a barrier, just like a single alpha particle? The stage was set for a new chapter, bridging the gap between the microscopic and the macroscopic. This conceptual leap required a theoretical visionary, someone willing to challenge the accepted wisdom about the limits of quantum mechanics. That person was Anthony Leggett. In the early 1980s, Leggett tackled one of the deepest questions in physics. Where does the quantum world end and our classical world begin? Schrödinger's famous thought experiment about a cat being simultaneously alive and dead was designed to show the absurdity of applying quantum superposition to large objects. But Leggett wondered if it was truly absurd. He proposed that superconducting circuits incorporating Josephson junctions were the ideal candidates to search for quantum behavior, like tunneling, in a macroscopic system. His reasoning was that the collective state of the trillions of Cooper pairs in the circuit could act as a single macroscopic quantum